Alright, hopefully you remember how we left the last video. We finished up by talking about some of the variables that affect the rate of a reaction. We talked about temperature, we talked about the presence of a catalyst, we talked about surface area, and we also talked about the concentration of the reactants and how the more reactant you have, the greater the reaction rate. Additionally, we talked a little bit about the process by which a reaction occurs, or the mechanism. Okay? Essentially, a mechanism is a list of chemical reactions that describe exactly how an overall reaction occurs, how its reactants interact. For example, if you have a reaction such as this one, it's essentially saying that you have 2 moles of nitrogen monoxide and 1 mole of chlorine gas. These 3 moles of reactant are going to combine together to form 2 moles of product. If you think about this at a molecular level, it's kind of amazing. You have all these molecules zooming around in space in a container, and they have to collide at exactly the same time, all with enough energy to react, and those collisions all have to be direct hits. This is because the energy of the collision needs to be enough to destroy the existing bonds that hold the existing molecules together, and it needs to be enough to reform the new bonds for the product. A good analogy for this is to imagine a room full of students. Perhaps these students are at a dance. Okay? Everybody's milling about, possibly dancing. In order for 2 students to meet up so that they can dance together, they need to find each other in the room, and they both have to want to dance with one another. Similarly, atoms in a container move about. However, they generally move about as molecules, i.e., they already have a dance partner. They won't react with a different molecule unless they collide with enough energy to separate them from their current partner and allow them to bind with a new partner. The collision won't be a good one unless it's a direct hit. If they just skim off each other, it will be like they bumped shoulders but didn't really collide, at least not enough to cause a reaction. This is called the collision theory. If you think about the reaction in this way, you can see how much more complicated the reaction process is than the original equation implies. The chemical equation makes it look very simple, but the reality involves a dance of many molecules, a ton of energy, and the perpetual possibility of the reactants not interacting with each other. This is where a mechanism comes in. A mechanism is a list of equations that represent all of the smaller steps in the process of reacting. For example, for the reaction we were just talking about, the first thing that has to happen is the nitrogen monoxide needs to break up. This might be just one step in the mechanism. A study of mechanisms reveals the importance that the reactant concentration really has on the rate of a reaction, especially if you consider a reaction at a constant temperature. The reactant concentration is very significant. Because of this, we can base our calculations regarding the rate of a reaction on the amount and reactivity of each reactant. We have it's a mathematical expression, which can be used to describe the relationship between reactant concentration and reaction rate. It's called a rate law, and it looks like this. As you can see, the rate of a reaction equals a constant K, right here. Okay. Here's our constant. And the constant is particular to a specific reaction as well as a particular temperature. Okay? Because again, we're implying constant temperature. We also have 2 reactants. And above, you can see this M and the N. These exponents for the reactant concentrations are called the orders. We have 2 major types of orders. One is the order of a particular reactant. For example, the order of reactant A is M. Okay? But we also have an overall order for the reaction, which would be the sum of M and N, or however many orders there are for this reaction. Okay? So we have reactant orders and overall orders. Okay? The orders themselves describe the exponential relationship between that reactant's concentration and its effect on the rate of a reaction. Okay? It is not simply from the coefficients of the reaction. Okay? Sometimes there is, sort of by coincidence, the order is going to be the same as the coefficient. but you can't rely on that. Really, the only way of looking at reaction and determining its order is with some experimental data. You simply can't just use the chemical equation. Okay. So let's go back to our original example. Okay. We go back to our nitrogen monoxide. We can draw a skeleton reactant or reaction rate law here. Okay. Because we do know the two reactants. Okay. And we can put M and N in place of the orders, and we don't know a value for K yet. Okay. But we can draw this rate law because we have some idea of how it's eventually going to look. Okay. Then we need to calculate or collect some experimental data that's going to allow us to finalize our calculations and figure out the orders, as well as our K value. Okay, so here's what the data is going to look like. Essentially what happens is an experimenter is going to design a lab in which you have multiple trials, 1, 2, 3, 4. Okay. What you do is you take the two reactants and you react them together multiple times, okay, in totally separate trials. In one trial, you'll change one of the reactant concentrations, but keep the other one the same. And you'll see what effect that has on the reaction rate. In this particular case, you can see that by doubling the amount of nitrogen monoxide, we quadrupled the rate. Okay. If you go down to a set of reactions in which the first reactant is kept the same and the other reactant is doubled, you can see its effect on the reaction rate. In this case, you can see that by doubling the second reactant, we were able to double the rate of the reaction. Okay. To do the calculations for this, what you're going to do is take the data and you're going to select two experiments, two trials, like we said before, where one reactant stays the same and the other one changes. And you're going to write the rate laws for both of these reactions. So if we write the rate law for the second one, we have a rate of 5.72 times 10 to the minus 6 equals K times 0.500 to the M and 0.250 to the N. That's the first one. And then if we draw the law for the second one, actually, I'm going to put it down here. If we draw the rate law for the second experiment, we're going to wind up with 1.43 times 10 to the minus 6 equals K 0.250 my decimal line. And actually, you should just sort of disregard that line. Okay. What you wind up doing is you take the two rate laws that you write from two sets of data, and you draw a ratio between them. You can see that I've put this line in. Okay. What this does is it allows you to cancel out some of the variables. In this case, we can cancel out our K. They're going to be the same in both equations because we haven't changed our temperature. We can cancel out the end of both equations because they're the same. Okay. And what that leaves us is a ratio between our reaction rate and a ratio between our concentration, all raised to a power. If you simplify this down, you get 4 equals 2 to the M. And then it's sort of easy to see that our M in this case equals 2. When we go back to our rate law, that tells us that what we have right now is rate equals K NO squared. And we just have to figure out now what N equals. Okay, so we're going to do the same thing with two different sets of equations. And that's hopefully going to allow us to calculate the order for the chlorine. So we're going to do that by selecting two equations in which you have the chlorine changing and the nitrogen monoxide staying the same. So let's select experiments 1 and 3. Okay. So in this case, we're going to have a rate of, let's see, it'll be 2.86 times 10 to the minus 6 equals K times 0.250 to the m. You can just leave it as an m even though we know it's a 2 because it's going to cancel out anyway. And that's going to be times 0.500 to the n. And all of this is going to be over 1.43 times 10 to the minus 6 equals k times 0.250 to the m, 0.250 to the n. Okay? So let's cancel out our terms that appear in both. We've got our k, we've got our k, we've got this, we've got this. And that leaves us with, if you simplify this down, 2 equals 2 to the n. You can see how that kind of simplifies down into the 2, and then you're left with the n. So this tells us that n is going to equal 1. So we can go back up to our rate law, and we can erase our n, and we can put a 1 in its place. Or you could leave it blank. It's implied anyway. Okay. So to finish up this, it is possible to still calculate our k value. Now that we know our 2 orders, what you can do is you can pick any of the 4 trials. Let's actually just go with the first one. And you can put in the data that you have. So if we put in our rate of 1.43 times 10 to the minus 6, we put in k, we put in our concentration, and we raise it to our order, and we put in our other concentration, and we raise it to our order of 1. Now we have only one missing variable, and we can easily solve for that. When you solve for this k value, you can determine that it's 0.14, or at least it should be. Okay, so it should be 0.14, and then you can put it in, and you can have a complete rate law for this particular reaction. Okay. This process is called the method of initial rates, and it's really the best way of determining the order of a reaction. Okay. And it's how you take experimental data and use it to determine the rate law for any equation. Now complete exercises 15.3 and 15.4 on page 683. We're going to collect this next class.